Okay, welcome everybody. Thanks for being here. It's good to be able to talk more about mechanics with you. How are things going? Okay. All right. So we're starting to get into the content that might be a little newer, a little fresher, and the problems might be taking a little bit longer. Um, and if you have questions, please feel free to use the group me. I understand if you have other modes of communicating. Nonetheless, I'm grateful that people are interacting very calmly. There's not much in the group me happening, so but feel free to use it as a resource and to share screenshots of things that you're working on or questions that you have as you proceed. So in terms of administrative actions or responsibilities or details, we have exam 1 a week from Tuesday. And this afternoon, what should happen is there will be seat assignments that we send out, okay? And as you know, most of the class is actually going to be on College Ave, and some people are going to be here still. This way, everyone has a little bit of space to work out or work on the exam. All right. If there's an issue with your assigned seating, so I talked with the TA and the grader, and they're like, "No, just make the assignments and have people contact you." I'm like, "All right." So that's what we're doing. All right. So if you cannot make it to College Ave and you have a good reason, okay, then send us a message. Send a message to me and to Praj, the TA, and we'll adjust things. Okay. Make sure you bring your ID to the exam. All right, and we'll make sure that we also have multiple versions of the exam out there so that people aren't tempted to do different things. Yes.
Will it be the same time as the class, or?
Yeah, same time as the class. Right. Just we need a lot of folks to go over to College Ave. Yes.
You said last session that
So it's going to be, we're going to send out the assignments, and if you have an issue with where you end up, which is I don't know how Praj exactly decided it, then send us a message and we'll sort things out. Okay. Any questions on that? We'll also send an announcement about the front and back of the sheet, the handwritten notes, the calculator, all that kind of stuff. All right. It goes through the material we're going to cover on Tuesday. Okay, so we'll have session 8 on Tuesday, and then the assignment that will be due on Thursday. All that material is fair game. So normal loading 2 is going to be would be the end topic, and then we'll have an exam. All right. The lab starts today, so there are 9 people who are there right now, getting to do the lab. Couple things. So last night, Professor Kim Cook-Chenault sent me a message saying, I want you to do this pre-lab survey. And I was like, okay, the labs start tomorrow. So there's a pre-lab survey now. In addition to the pre-lab safety certificate, I understand. There's a lot of stuff we're asking of you. Okay. Thank you for cooperating. The TA then just told me, you really should tell them that there are videos to watch before they go to lab. I was like, oh yeah, that's probably true too. It makes the lab go more smoothly. So if you go where? If we go to, just so you have an idea, and it's right. He's right. It will save you time in the in the short run, I guess, because it's only an hour and 20 minutes. But if you go down to the bottom of the page for mechanics and materials, you can go to this MechMat tensile testing and design lab, and you might take a look at these videos to get an idea of what we're going to be doing. Okay? And there is also a collab there that will help calculate things like modulus of resilience, modulus of toughness, elastic modulus. All those things and how you do that, how you make those calculations are here. There are also the questions, all right, that you can download beforehand if you want to get a head start. On Canvas, what you'll be responsible for with the lab is in the bottom of the home page with all the modules. I think it's right above attendance. Okay, so you're going to want to be operating down here. Okay, and so now you see we have this pre-lab training certificate there. And now there's this pre-lab survey. And you don't have to finish all these questions before you exit the lab, but it's kind of in your best interest to do, make sure you have all the data for sure. And you ought to actually be able to pretty much do it. Okay, if you might take like 10 minutes extra or so, okay, but I think you can really get it all done. And then there's a post-lab survey now as well. Any questions on the lab? Yes?
I took the lab safety course, but I don't think that I ever got a certificate of completion. That's supposed to be notified like an email or something?
Yeah, you should have gotten one. So if you didn't get the lab safety certificate and you took the refresher as Alex Ruiz instructed, then yeah, contact him and CC me, and we'll go from there. Okay, all right. But you know, and you can put that as a screenshot if you need to. You know, if you feel better about that for now. Okay. Thank you for bringing that up. I don't. Again, they're interesting things. So far, we haven't. Now, knock on wood. This will be the day, right? But so far, you know, there've been kind of individual one-off issues, and they seem to be one-off, weird, quirky things. But please, if we get into situations where, you know, like one of the questions is really wrong, speak up. I mean, I make mistakes, okay? And we'll try to get it worked out. Yeah. Any other questions? All right, let's get into the flow. That's survey, Surf 9. Okay, anyway. So last time we discussed material properties, and we talked a little bit about things like modulus of toughness, modulus of resilience. Right, here they are, right? Poisson's ratio. We also discussed this general approach to solving mechanics problems, where you have equilibrium, geometric compatibility, and constitutive equations. We talked about linear elastic, perfectly plastic material models, and linear elastic, linearly plastic / strain hardening models. Okay, so that is actually quite a bit if you think about it. Okay, but those terms now are those specifications are pretty powerful in helping us understand how a solid is going to respond under loads. Okay, under stresses, under forces, in a structure. Today, we're going to kind of continue a little bit in terms of describing additional metrics, okay, or different ways we can characterize how a load affects a solid, and we'll introduce the bulk modulus, okay, which is a material property, and it is also dependent on the elastic modulus and the Poisson ratio. Okay, and then we'll get into distributed axial loading, and all of these things, they are under the general category of normal loading. Now you're like, wait, we already did axial loading. Yes, we did already do axial loading. Okay. Before we even go further, what could be a difference between axial loading and normal loading? What could be a difference? Or maybe I can even say, what would be a difference between uniaxial loading and normal loading? Yes?
The amount of forces on it.
The amount of forces on it. Can you be more descriptive, Mark?
The axial is normal loading.
That's right. Okay, so what Mark is saying there is uniaxial or axial loading typically describes a normal force acting on one pair of faces on a, let's say, a 3D element that we're interested in. But normal loading could be acting on multiple of those faces at the same time with normal stresses and normal forces. Okay? Now, maybe we discussed it a little bit, but what is a pretty big example? How do I say this? What is a type of loading that is normal in nature, but not just uniaxial? Okay, I think Mark knows, but anyone else? So a type of loading that's not just uniaxial, but it's acting on faces normally. So I'm acting on more than one face at a time of a material element or of a structure. I thought I heard someone, come on, who's murmuring it? Who's whispering? I heard it. What did you say? Huh? You can speak louder. Okay, I thought I heard someone say pressure. Okay, yeah, pressure, right? Or hydrostatic loading. So we've talked before about, dropping a rock in the ocean, okay? And as it goes further down, right, as it gets deeper and deeper, as the depth gets larger, that would be an H. We do rho g times H, and that's the pressure surrounding the object, right? So that hydrostatic loading is something that we often associate with normal stresses. Okay, so now if you had that box, okay, or that cube under pressure, okay, like David Bowie, right, and Freddie Mercury, right, it's under pressure. We could think about, okay, how is that box changing in its shape or in its volume? Okay? And let's start with a box. Okay? So here's a box. It has coordinates x, y, z, and it has some volume. And when we define the volume, okay, what do we can say, since this is a really small element box, we'll just say that it has lengths dx, dy, dz, right? So the initial volume is just V naught. Now, what if we apply normal stresses to this box? Okay, so what are we saying here? We're saying that we've now applied a sigma x, a sigma y, a sigma z, okay, to the pairs of faces that are in those particular directions, and the size of the box is changing, right? We're saying that, okay, we've got sigma x acting outward and stretching this way, sigma y is stretching it this way, sigma z stretching it this way. We have, as you can imagine, a change in volume. So we'll say that it's V naught, the new volume, right, is V naught plus delta V. And if we write out the change of lengths, all right, that are contributing to that new volume, this may look a little weird, but we can write them out as 1 plus the axial strain and quantity, right, times that original length. Does that make sense? So, right, because remember, strain is the change in the length over the initial length, right? And it's kind of, maybe it's easier to think, okay, this is the percent increase or percent decrease, all right, of a change in of length, okay? And so, it's not 100%, it's like, 0.1%. So if I want to see the increase, right, I got to do 1 plus that, so that's the 1 plus the epsilon, right? That quantity. So maybe like I have a 1% increase, so now I have a 101% increase. So I do 101% times my original length, right? And that's the new length. So that's all this is saying. What's the new volume then? Well, V naught plus delta V can be given by the product now of all those new lengths. Isn't this fun? All right? And so you get this fairly large expression. And the delta V, right? So remember we had V naught plus delta V. So delta V minus V naught, or this V plus delta V minus V naught would give us just the delta V. And the delta V is the change in volume, right? So the change in volume ends up looking like this enormous expression. Okay? And then we can write this is this minus 1, okay, times this. And we can approximate. So this is not exact, right? But look, you're going to have some, if you do this all out, right? 1 is, well, 1. 1 times 1 is 1, right? But these epsilons are small, okay? So if you do like epsilon x times epsilon y, right? If you have these other terms doing FOIL or doing FOIL twice or distribute, however you want to look at it, once you have an epsilon squared term or an epsilon cubed term, those are small relative to everything else. So what we're saying is we can ignore those, and in the end, what we get is approximately equal to this quantity of epsilon x plus epsilon y plus epsilon z times the original volume. Now, dilatation, this is a term that describes the volumetric strain. Okay, so we've talked about axial strain, right? That's the epsilon y, that's the epsilon, or that's the epsilon x, epsilon y, epsilon z. Volumetric strain is going to be like it defines here. What's the change in the volume divided by the original volume? Okay, so it's like a volumetric strain. Well, how else can we describe it? So look at that. If I take this delta V, right, and I divide by V naught, that one right there, these dx, dy, dz's go away, and so you get epsilon x, epsilon y, epsilon z summed together, and that's the volumetric strain. I would be tempted just to multiply them against each other, right? Because if I multiply them, right, that's giving me a volume, but no, that's not how you do it, right? We just saw that you had to do 1 plus the epsilons, right, to be able to get the new volume, right? And we're saying we want the change in that volume over the original volume. Okay. Now, how do we relate these or this volumetric strain to the strains that we know and love, the axial strains? Well, we write out this constitutive relationship that we had last time. Okay, so we have epsilon x is equal to 1 over e, right? So if sigma x is positive, then epsilon x will be positive through the elastic modulus. And if you have orthogonal stresses that are positive, well, that's going to cause a collapse in the x direction, right? That's all these equations are saying, and we put them in matrix form. Okay, so now, all right, it turns out that if we do epsilon x plus epsilon y plus epsilon z, okay, that's what this is approximately, and that's what the dilatation is, that's what the volumetric strain is, okay, then this is what you get. And you can kind of see it, so all we did is we added all 3 of these together. But you see the 2 new comes in because there are a nu and a sigma y here and a sigma y, but there's no sigma y here, right? So we got to subtract 2 sigma y's. Just like there's a sigma z and a sigma z, we got to subtract 2 sigma z's in the Poisson ratio. And we had to subtract 2 sigma x's in the Poisson ratio. So that you can kind of see how this plays out. And we just have a dominant 1 sigma x, right, in this for the epsilon x. Any questions on this? I should probably write that dilatation, this is just another way of saying And I think on the next slide it says it, but this is volumetric strain. Any questions on this? Okay, so there it is, volumetric strain on volumetric strain. Okay, and that's what it's defined as being if you have a sigma x, sigma y, sigma z. Now, hydrostatic loading is essentially what we said about putting an object underwater or putting it in a vacuum chamber or putting it in a pressurized air chamber, right? That's going to be hydrostatic loading. Anyone that's flown on an airplane has been loaded hydrostatically, right? Anyone that's jumped into the water or gotten their head under, like, you know, I don't know, I think I'm too big to get my, or maybe better said, the tub at home is too small for me to fill it completely and have myself completely submerged, right? But if you even if you don't know how to swim, which if you don't know how to swim, don't do this experiment, right? You've gone down. Okay, so if you know how to swim and you've gone in a pool that's like 6 feet deep, right? What happens to your ears when you get down at 6 feet, right? You feel it, right? You feel that pressure on your ears. Okay, that was unrelated. All right, so with hydrostatic loading, what we have is that all the stresses on the 6 faces are the same and they're inward. So there we have negative values, at least if we're defining sigma x, right, as being positive outward and sigma y as being positive outward. Okay, and so that all of these values, they just equal p. And so if we want to describe the volumetric strain in terms of pressure, right, we just plug in the p's here, right? And so we get minus 3p for this term, and the rest is as we had it before. This quantity is somewhat interesting, and we can describe a relationship, okay, that's kind of like Hooke's law, right, for uniaxial strain. So remember, and uniaxial stretch, right? Remember, Hooke's law for uniaxial stress and strain is just sigma is equal to E epsilon. Okay? Well, we're going to say instead, okay, right here, that P, so this is the sigma, right? P has the same units as sigma, is equal to minus K times the volumetric strain, right? So before we had, right, the analogy here, analogous to sigma is equal to E epsilon, right? So, you know, this, right, you can see how they map. P goes to sigma, volumetric strain goes to uniaxial strain, and K is just like E, all right? Except this is going to be describing, of course, the bulk modulus, and will allow us, right, to relate volumetric strain to the pressure acting on all sides. Okay? And this bulk modulus has units of force per area, so again, it's like stress. And there's a relationship here, okay, that we get. So you saw this, right? That if we manipulate things a little bit, we can say, or if we just do this minus P times V naught over delta V, right? This is PE, right? Then it's going to be this relationship right here, like that. And so the bulk modulus is equal to the elastic modulus over quantity 3 times 1 minus 2 nu. This is not an expression that I go home and remember, to be honest. Okay, and I don't really drill volumetric strain. Maybe we could do a problem this time. We'll see. I don't know. But usually, I don't emphasize this topic too much. But it's good to know. It's for your good to know file. And you'll see that bulk modulus comes up in a variety of mechanics types of problems as you get more advanced, I guess. And it's particularly relevant to rubbery materials. Why is, yes?
What's the symbol called again? 3 times 1 minus 2.
This is called nu. That's the Poisson's ratio. Okay, it's like a weird looking scribbly V. We call it nu. You can write it in your Colab script as NU, nu. Okay. Now, what is interesting, or there are multiple things that could be said to be interesting here, but one thing that is interesting is if nu is equal to 0.5, guess what happens to the bulk modulus? Right? It explodes. You end up having something over 0, so that gets to be infinite. Right? This is kind of interesting, especially in the context of the materials that we study. Most of the materials in this class, the Poisson's ratio is going to be 0.2 or 0.3. Okay, that's for the steels. Let's go into this. Okay, here we go. So here's just a little Colab script that plots some of our favorite materials: aluminum, steel, and rubber. Polycarbonate. Okay, I like polycarbonate. It's not one of my favorites, but it's a good material. It's got a really great impact strength, and it's often used in protective windows and shielding. Okay, and in helmets. Not used as much in water bottles anymore. Yeah. There's a little thing called bisphenol, right? Another interesting thing about it is it's actually sensitive to UV light, so you have to put in special additives to make it more resistant. Okay, so it's a great material. I don't know why. We can nerd out on different materials, I guess, and I'm sure you know materials that I don't know. And my daughter would say, "You're just showing off, Dad," like if I say something technical, right? So anyway, I'll stop showing off. But polycarbonate is good. Notice that its elastic modulus is very similar to that of silicone rubber. Okay, so like a couple of gigapascals. That almost seems low to me, but that's what we have here. But the Poisson's ratios are very different. Okay, and we see here, okay, that because the Poisson's ratio of silicone rubber is close to 0.5, it has a much higher bulk modulus. Okay? And let's go back. What does that mean, really? What does a high bulk modulus mean? What does a high elastic modulus mean? Right? Sigma equals E epsilon. If you have a high elastic modulus, right? What does this mean? It means that you've got to put a ton of stress in your material to get some notable strain, right? Because the sigma equals E epsilon, so sigma over the E is the epsilon, right? Or vice versa. A little bit of strain puts a huge amount of is equivalent to a huge amount of stress. So you can kind of think of it as a resistance, but that's probably not a good idea. Okay, it is elastic modulus, right? But that's what we're getting at. So if you take a piece of rubber, let's go back to this, right? So large K, right, is meaning that if you put in, you have to put in a ton of pressure, a lot of pressure, a ton of pressure. That's a bad thing to say, right? Why? Because ton has units of newtons or units of pounds force. A ton of, right? But, okay, you got it. All right, you put in pressure high, okay, and you get low strain. So that might be kind of counterintuitive, right? Because rubbery is just a rubbery, right? But there's actually very little volumetric strain underwater. Who or what takes advantage of that? The little fishies. Did you say that? You said the little fishies, right? Right, because they're rubbery, right? They have these rubbery qualities. They know how to process the foods that they eat and make the oils and whatever, right? And to get this like kind of rubbery thing. So they don't care, especially because they got water inside them, right? As well. That's a good thing with their mouth, right? Because otherwise, if they were just air inside, that could be problematic. right? They're or variety of things. So anyway, it's just fascinating, right? That the silicone rubbery material, because it has a high Poisson's ratio, right? And what does a high Poisson's ratio mean? High Poisson's ratio means that if I pull in one direction, I get a lot of contraction in the other direction. Or if I push in one direction, I get a lot of expansion, right? That's what a high Poisson's ratio means. And in particular, volume is conserved when the Poisson's ratio is 0.5. Okay? So that means if I push in over here, I might change shape, but the whole geometry conserves its volume. Not so much with these other materials, the ones with the lower elastic volume. Okay. Any questions on that? All right. So, any thoughts? Maybe your appreciation for rubbery materials has gone up now because they have a high bulk modulus. And you don't want to mess with some of these because, that's very vague. All right. I'm just thinking about O-rings. They're often made out of rubber, Viton, silicone, whatever, butadienes, these types of materials, right? And they actually also are temperature sensitive. And so we use them. They're good because they conserve their volume, and so they can seal around an object, right? Like in the solid rocket boosters of the space shuttle. All right? But if it gets too cold, it will lose some of its elasticity. It becomes stiff. Feynman put an O-ring in cold water to demonstrate this principle, that it becomes stiff, and that can cause issues with sealing and people's lives. So rubbers have a very special material, and we need to take care of them when we use them in design. And there are booklets and things on how to design O-rings, and they're actually I think there's a little bit of art, to be honest, when you start playing around with the rubbers. Yes.
How do we differentiate between the K for the bulk modulus and the K for the spring constant?
I'll tell you that one's the bulk modulus and one's the spring constant. No, they're not. They're definitely not. Right? So spring constants K, those are going to be newtons per meter. All right? And this one, as we said, is in units of pressure. Okay, so newtons per square meter. So definitely not the same. Thank you for that clarifying comment. If we drop a block made of aluminum, okay, with each side having a length of 1 meter, and it goes up to a pressure of 100 atmospheres, okay? So that's pretty deep. All right. What is the change in the volume of the cube, and what is the change in length of one side of the cube? Finally, what would be the equivalent depth underwater to get to 100 atmospheres? Okay, so let's do some drawing, some calculating, some thinking. All right, and we have here our lovely cube, and thankfully it's a cube, so that all its sides have the same length, L. And we're just writing things down now. So we have a pressure of 100 atmospheres. We have a bulk modulus of about 69 gigapascals. And there are questions about, hey, what's the change in volume? What's the change in length? And what's the depth that we've gotten to? So here is the pressure acting on that box, on that cube. And let's kind of break it down into the 3 columns. Okay. And sometimes, sometimes we're kind of making a round hole fit into a square, I feel, when I write these 3, okay? But nonetheless, they do help make sure that we've got the necessary elements addressed to work on this problem. So for example, do I need to really draw a free body diagram to show that the cube is not accelerating? Probably not. Okay, so, but that's equilibrium for you. Geometry, you know, it's kind of helpful, I think, to write this out. Okay, so we're squishing on every side, and in this case, it's not a rubbery material, right? But I mean, it can have a high bulk modulus, but it is going to be going inward because I've got stresses pushing it in, and the Poisson ratio is causing that to happen, and you know there's going to be less of the lateral contraction or less lateral strains than there will be of the actual axial strains. So we can write out that the volumetric strain is this delta V over V naught, and we could think of that as a constitutive relationship if we want, or you could think of that, or you could think of that a geometric relationship, really, and maybe it should go more under geometry, okay? But this is definitely a constitutive relationship, right? Anytime we write out something that's Hookean, all right, we put it under the constitutive side. And what do we mean by this? Hookean would be describing anything that describes a relationship between a change in geometry and loads, all right? So it's like the one thing, it is one of the big things that you did not do in statics. Okay? You did not talk about deformation. And there are problems that you could not solve. All the problems you solved had to be determinate, meaning through equilibrium, you were having the same number of unknowns and a number of equilibrium equations, right? But now we're like, oh, guess what? You may not have that, right? And I think you saw that now, you've seen that a couple of times now with these bars stuck between walls. These are indeterminate systems, so there's no way to solve them purely by equilibrium. Anyway, I digress. We have now a way of writing out the change in volume, right? That's the first thing they want. Well, it's just EV. It's not an electric vehicle, but it's EV naught. And we can rewrite that as minus P V naught over K, all right? So just using the definition of E, right, and substituting it in. Here we have, again, volumetric strain, all right? And we know from our previous work in Slideroonies that we have epsilon x plus epsilon y plus epsilon z. That's what the volumetric strain is equal to, or approximately equal to. And in this case, because it's hydrostatic loading, they're all the same. So it's just 3 epsilon x. So we can also write over here that epsilon x is equal to E over 3. Okay? And the okay, so check. We got an expression for delta V, right? Now we're working on getting an expression for delta L, right? Because they wanted us to say, hey, how much is this material changing in its length? So that's why we're looking at the uniaxial strain, or the axial strain, better said, because we have multiple strains in 3 directions. All right, so the change in length will be given by this L naught times epsilon x, and so we can now write that it's going to be L naught E over 3. Pressure, all right, underwater. This is back from physics. We won't derive this necessarily, okay, but you can think of it as just the density of the water, or whatever the liquid is, times gravity, wherever you are in the universe, hopefully on a planet or something that has gravity, and or significant gravity, I guess I should say, and then a change in height. That's going to be equal to the pressure. Okay? So the pressure is equal to P over rho times G. And we can plug these values in, and what do we get? We get that the change in the volume is that number, minus 150 centimeters cubed. The change in the length is about 50 microns. And to get to 100 atmospheres, you got to be 1,000 meters underwater. Any questions on this? Yes? Okay, good question. All right, so when you start talking about 1,000 or 100 atmospheres, doesn't really matter, right? Because it's like 1 atmosphere versus 100 atmospheres, and you're like, okay, 99 versus 1%, right? But typically, yeah, we're thinking more in terms of gauge pressure. So what is the relative pressure that you would have between, and this becomes more important when we look at pressure vessels. Like we care about the difference in the pressure between the inside and the outside. But here, everything's under the same pressure, quite frankly. Right, so maybe I'm confusing people, right? The inside of the box, that's solid, the water, it's all at the same pressure. There's no change in pressure. What you're referring to is it 100 atmospheres relative to atmosphere at sea level, or should I tag on another atmosphere because there's 1 atmosphere at sea level and then I've got 100 atmospheres underneath, right? So it's like 100 versus 101, right? That's what you're getting at. And the gauge pressure. Any other questions? So write these things on your formula sheet or on your sheet of notes, and it's a lot of it, quite frankly, with these types of problems, with the ones on volumetric strain and dilatation and bulk modulus, it's kind of just like looking at the equations and substituting things. All right, but they do make sense, and there is physics behind what's happening. All right, so there will be a question on the assignment for you to pursue. All right, this topic tends to be a little bit more confusing, and it's important. All right, so this topic definitely is fair game. All right, you can take a look at I think it was there are problems from the 2015 exam 1. All right. And that problem was probably a little bit rough, okay? We'll actually go through some of it today. I changed the notes a little bit to cover I have like 3 examples that I think are kind of interesting. The third example is maybe less relevant. Well, it's relevant. It's relevant to a particular area, but the first 2 examples are definitely for reals. Okay, so axial deformation in a bar. Have we already covered this? In some respects, yeah, right? We know how to calculate the delta if you have a load, uniaxial load, right? So that's not going to be too new, but we're going to introduce a new equation that you can use to show the same thing that we already knew. What am I talking about? I'm talking about delta equals pli or delta equals fli, right? So the delta is equal to the PL over quantity EA, all right? But we're going to introduce a new equation that kind of helps us in a more general case to solve for this deformation in a bar. And if you like, you can go to Hibbler's book, chapter 4, and you can see the derivation. I'll do kind of a derivation now that maybe is, I hope is somewhat illustrative of how we relate the uniaxial strain to the changes in length. So this problem, okay, we're not doing bulk modulus anymore. Wipe it out. Okay, now we're just talking about stress in one direction. Okay, Harry Styles and all those people, they're having a good time. It's one direction, and it's beautiful. All right, so we have P here, and it's just pulling this bar apart, and it has initial length L naught, and we know it's going to get to some new length. We'll call it L nu. Okay, what? Was there a question? No? Okay. All right, so L nu and the delta, right? This difference between those two, lengths is what we'll call the delta, and we can think of this delta in terms of a strain. Okay, and this strain is something that we can relate to the stress through Hooke's law. Okay, we have an E epsilon. And we know that the stress is just P over it. All right. This is really review. Okay, this is very much review. All right, so don't panic. Okay, just showing how we've thought about defining strain and displacement or deformation in a uniaxial loaded bar. Okay, and so we can write sigma over E, and we can say that's delta over L naught, and we can say that's equal to P over EA, and you know the rest. Delta is equal to P L naught over EA. All right, so we've seen this before. And we've just derived it. And we derived it pretty much just by using the definition of strain over and saying, hey, the strain that you have in this long bar, yes, that strain is going to be the same throughout, okay, for this particular case, because the force is the same throughout. It doesn't have to be that way. We'll show you in a second when it's not. Okay, but when the force is the same throughout that bar, this is a great way to calculate what the displacement is. And now let's go and break it down a little bit more. All right? Let's look at a chunk of this bar. And let's say that that chunk has the same forces on either side. All right? And it's in tension, we'll say if P is positive, and it has a pretty small width. Right? We'll call that dx. And if we look at this little chunk and we look at the amount that is being pulled apart by this force, by this internal force P, we can say that it has a little, not a delta, but it has a d delta. Right? You get where this is going. Okay? We've broken it down into a small element, and we have a little amount of strain there. Well, guess what? The bar has a lot of these little chunks in it, right? And I can think of lots of d deltas along it, right? And they're going to sum up to being the overall delta, right? So you're like, oh, that's Riemann sums. Okay, great. That's sums, right? Or if I go like mini, right? This is integration, right? I'm integrating all these little chunks, okay, to get the overall displacement. So you see this expression is almost meaningless, right? But it's helpful to us to think, all right, the overall displacement is going to be related to the integral of all these d deltas, right? And now, what is delta? Or what is d delta? Well, d delta, all right, is going to be related to the strain that this material is experiencing, okay, the uniaxial strain. So we have epsilon. This is just the change in the length over the length, right? Except now we're at the micro level. And epsilon is still an epsilon because it doesn't really care about the size, right? But now we're saying this is the strain at a micro level or a nano level, whatever, very small level. So we go ahead and we say, okay, well, d delta is equal to epsilon dx. And if I look at the definition of epsilon, right, that just goes back to Hooke's law right here, right? Epsilon is equal to sigma. Epsilon is equal to sigma over e. Plug that in. I know what sigma is. That's p over a. And now I have an interesting integral. Okay? The integral across this whole thing from 0 to L of p over EA or p over AE dx. Right? And this is an equation that you want to write down. Okay? Now, this form is, I guess what Hibbler uses and maybe more widely accepted. They just say, okay, look, it's not p times x, it's not a times x, it's just that p can be a function of x. A can be a function of x. So now, right, we've got something kind of interestingly powerful. This pli equation is just when you have a constant cross-sectional area and just when p is constant. Okay? But this equation is applicable to an internal force. So we think of p of x as a force internal to the bar and a as being a cross-section. So now, if you were given a problem where it says, hey, look, this is the function that describes the cross-sectional area as we go along with x. Maybe it's a cone. Maybe it's a, I don't know, whatever it is, okay? But maybe it's a sinusoid, right? as long as you have a function of it as a function of x, you can put it in there. Now, if it's a function of x, that's a bummer because now you're integrating with respect to x, right? So you had to integrate it appropriately, right? But if a is constant and p is constant, then it's just px and then 0 to L for that x, right? And it just spits out this thing again, PL naught over EA, okay? So there was one other thing I wanted to say. And I think that's, yeah, we're good. We're good. Just that P is a function, P is an internal force. Okay? So let's look at a system of a hanging bar. And this is an instance, right, where we have gravity acting over the bar. Now, before we even do this problem, let's think a little bit. What do you think the force looks like in this bar? Internal force. What do you think it looks like? Okay, so it's going there. Okay, downward. Yes, what else? Can you be more descriptive? Internally. Well, my first question is, and you kind of know this answer probably already because I wouldn't have asked it, is that force constant along the length of the bar? No, it's not. All right, so that's first, right? Not constant. But let's just think about it for a second. Up here at the top, maybe it's easier to think of it that way. How much force is the wall putting on that bar to keep it from falling? Yeah? The weight of the bar, just mass times gravity, right? So at this location, right here, right, there's got to be an equilibrium. That external force is going to be equal to the internal force, like right next to the bar, or right next to the wall, sorry. Okay? You see that? And that makes sense. I mean, anyone is like, that's like saying, hey, I'm holding this object here, right? How much force am I putting on it to hold it? So like, it's just the mass, right? So it's just the whole mass of this thing times gravity. That's what I mean. It's a weight, right? Be careful. Not, it's not kilograms. It's not slugs, right? It's a weight. What about down here? What's the force like there? Yeah, go ahead. Well, what do you think about that? Remember here, it had to support all the weight below it. If I come up just a little bit away from this edge, how much weight below it is there? Huh? Only a tiny little bit, okay? So it turns out, right, that if I'm looking at the internal force of this bar hanging, right, we're no longer doing the uniaxial test where I've got a force that I'm applying on both ends, right? And when I do that, of course, yes, the bar is hanging from the top clamp, but I'm applying so much more force to pull it apart that I neglect gravity when I put it in the material testing machine. Okay, is that clear? Right, because the mass of these objects compared to the weight of these objects, right, I'm messing it up, the weight of these objects is so much less than the amount of force that we're putting on it when we do the uniaxial loading normally, okay? So, get it, double entendre, when we do the uniaxial loading normally, like regularly and, okay, never mind, okay, not that fine. All right, so we have an interesting perspective on what the force might look like. And you're like, is it linear? Well, probably so, because what? Because, well, it's 0 here, and it's going to be mg up there. Okay, so you've got this idea that it's going to vary linearly. Let's go and break it down into our 3 categories: equilibrium, geometry, constitutive equations. Let's start with equilibrium. We're going to spend probably most of the time looking at equilibrium here. What's the first thing you do when you get an exam problem and there's a statics question? What do you do? Huh? Equilibrium, yes. And specifically, external equilibrium. Okay? So let's look at external equilibrium. We already kind of talked about this, right? But the external equilibrium is with two forces. The wall pulling up on the rest of the bar and gravity acting on the bar at its center of mass, we'll say. Okay? Now, it's acting at the center of mass, all right? But don't be confused. That is not like when I look at this thing internally, it's only acting there, boom, that's it. No, these are the external, this is just an external equilibrium that we're performing here. Okay? So we know that R is equal to mg. Okay? Now, what did I write there below it? Rho g LA. Okay? This is a weird one. You're like, what? Well, you remember we were hanging those pieces of acrylic in the homework, right? And we said that in order to calculate the weight, you had to do length, right, times width times height, right, to figure out the volume, and then you multiply by rho, and then you multiply by g. This is the same exact thing. What we're saying is there's a length to this, and we have a cross-sectional area, and we got to multiply by the density, and we got to multiply by the g, right? And that will give us this mg. Next, internal equilibrium. And this is maybe a little bit trickier. Okay, actually, I will say it is definitely trickier. Look at this. Okay. I take a slice, and for now, I just draw a distributed force, right? What are the units of distributed force? Like lowercase f? Newtons per meter. Who said that? No one want to claim it? Oh, you said, okay, Mark. All right. So, newtons per meter, all right? Remember, we care about the internal force. Why? Well, I guess maybe we should ask the question. We want the change in length of the bar, right? That's what we're trying to do, okay? And so we want to use our new handy-dandy equation, right? That delta is equal to integral of p over EA dx, right? So that's what we want to do. So in order to use that equation, we need to calculate what the internal force is. Okay? And so in order to do that, we do a slice. So here's the internal force, P. Here's a distributed force, little lowercase f. And there's the R. Okay, Axial. So we already know what R is. Okay, we have this idea here. F, let's think about it. All right, so F is going to be a distributed force. And we can think of this F as this lowercase f, right, as then contributing, okay, to create a large force, okay, or a complete force over this length. Okay, so as we go down, okay, from 0 to x, we are going to be integrating, okay, from 0 to x, this distributed force. And so this distributed force now, okay, it has units of newtons per meter. Well, guess what? Remember we just wrote down this force of rho g LA? Well, now we're talking, take out the length component, all right? And so it is going to have units of rho GA. You see that? This distributed force, if I just take out the length, I get rho GA like this. Okay? And this, you can kind of think of it as, hey, what is this distributed force? Like, I've got some density, I've got some gravity, and I just have the cross-sectional area. And so, you know, what is that distributed force? Essentially per unit length, right? And the length is in the vertical direction, so I'm using the rho, the g, and the cross-sectional area. Yeah. Right. You can think of it that way because that's what equilibrium tells us, right? So let's do it out. We're going to sum the forces in the x direction, and let's say this is the x direction, right? So P is positive, F is going downward, That's positive, but R is negative. So we have P plus F minus R, right? So like you said, P is the rest, right? What is P going to be equal to? It's going to be equal to R minus F, right? And so R minus F, right? This is the R, and we just calculated out that rho g AX is the remaining, the leftover, or not the left, it's the force, right, from the distributed force, okay? We did that integral out, and so we get this expression. You see that? So, does this make sense? If x is equal to L, right? So remember we said at the bottom, the internal force is 0, right? So when x is equal to L, it's 0. When x is equal to 0, up here, the internal force is rho g AL, which exactly balances out the rho g LA, all right? We calculated for that reaction force, okay? This is a little confusing. The most confusing thing is what to do with the distributed force. I think that's the most confusing thing, right? And so this idea that you have a rho g A, right? That's like it's like a force per length, right? Not force divided by area, but a force per length, right? And that is given by rho g times the cross-sectional area. Okay, that's probably the most confusing part of this problem. What do you do next? Well, for the sake of going through the columns, here's geometry. I mean, sure, the delta that we're interested in for the entire beam is going to be the delta at x equals L. That's like almost not even necessary to write, okay? But that's I just put it there, okay? Constitutive equation. This one we do want to write, okay? So remember, Hooke's law, plea, right? These equations, and now this new one with the integral form for displacement as a function of axial loading. This one we can write out as our constitutive equation. What do we know now, though? We know P, and P is a function of x. We know A, all right? It's just given as cross-sectional area A, all right? It's constant. And E is given as an elastic modulus, right? So we've got everything we need. And if we do not put in, right, before we just had a constant for P. So it was kind of trivial that it was just going to be PL over EA. Now our P is in terms of x, so the integral is non-trivial, but not that bad, right? So we can say that the delta is going to be the integral from 0 to L of this whole expression, right? And don't forget that you had to integrate this constant, the rho g AL, right? That's a constant, so we have an LX, and then we have 1/2 x squared, and we go from 0 to L. The A's cancel out, interestingly enough, and this is kind of, it's not an expression that I go home and think about every day, but it's kind of let's say it's somewhat famous. I don't know. There are probably many somewhat famous people. This is a somewhat famous equation. Any questions on this? All right. So, this is essentially the equation that would tell you how much taller you would be in microgravity, right? If you say in microgravity, if I'm in orbit, I have not this gravity, right? So, and if I assume that I have some elastic modulus and I have some density, right? And I'm somewhat, and all these assumptions, right? That I have a somewhat uniform cross-sectional area, right? I could figure out how much I'm shrinking, just because of gravity. And my understanding is that we're supposed to be taller at the beginning of the day than at the end of the day, right? And sometimes when I get into the car, psychologically, I'm like, oh, I got to back up the seat a little bit more because it's the beginning. It's in the morning. I'm taller right now. I don't know. I think that's just psychological, and it's probably because I wasn't wearing shoes a few minutes before I got into the car, and so now my feet are like, Anyway, but do you ever think like that? I'm like taller, so. Or maybe I'm just standing up taller, right? In a mirror, I gotta adjust everything. It's like, yeah, it's a great day. And then at the end of the day, I don't know what happens, but I guess I'm just slouching. Okay. Let's do another one. We have time for one more. All right. This one is a doozy. I should not have put this on the first exam, or the first test, or the first exam that I gave to the students ever in mechanics and materials. But you can see it. It's 2015, question 1. All right. But I was excited about it. I was like, yes, this is awesome. You can figure out how much. Well, actually, what is this question? What is a real life application of this question? Just read it and think about it for a second. What is a real life application of this? Yes. Centrifuge. Yes. Good. Yes. Yes. So centrifuge, and what else? What are some? What else? What else? That it is. Yes, it is. We're dealing with a centrifugal load. So yes. Any other applications that come to mind? Yeah, wind turbine, right? Exactly, right? So you've got these vanes that are coming off, right? And you're spinning pretty stinking fast, and they're really, really, really long, and you don't want them flying off and breaking. Okay? So this is kind of your first order pass to do this. And at some point in class, I think I'll take some time to tell you about what my PhD research was. But I looked at how bubbles move in a centrifuge. That was my research. Trying to degas silicones, actually, get rid of bubbles. So I got to learn things about bubbles and how to get rid of them. So we were spinning things. It was actually a pretty fun experiment. It was a little bit scary. Back to that polycarbonate, I had like this polycarbonate thing made out of, that was supposed to be bulletproof, so that if the centrifuge exploded, like it wouldn't hurt anyone. Okay, so it was pretty cool. It was pretty fun. In retrospect, like we haven't run the centrifuges as fast as I ran back then when I was by myself. I probably value other people's lives more than I value mine. No, that's not. No, I also I was pretty careful. But it turns out you can use lower angular velocities, and still get very good results. Okay, so this is spinning about this axis over here. We have some angular velocity, and we're going to talk about moving from the outside in. Once again, though, where do you think the internal force is the lowest, and where do you think it's the highest? Someone? If we're thinking, now we're talking about axial force inside. Where is the internal force the lowest, and where is it the highest? Okay, say that again. Michael? Or who? Okay, so at the end here, it's going to be what? Okay, so you're saying it's going to be highest here. Okay. Who agrees with that? Who thinks? Go ahead. You can close your eyes so it's not embarrassing. All right, close your eyes, and I want you to raise your hand if you think, so that you can't see other people. All right, so you're not ashamed, and you can be bold. Come on, close your eyes. Don't you guys close your eyes when I don't ask you to close your eyes? All the time you're sleeping, and now I'm asking you to close your eyes, and you can't do it? Come on, close your eyes. If you think it's highest at this end, where x equals 0, raise your hand. Okay. All right, thank you. Put your hands down. All right, that's fine. Okay, so it turns out a minority of you thought it was the highest there. All right? And so most of the class is correct. It's not the highest there. Okay? Again, just like that bar that was hanging, right? Remember we said it was hanging under gravity? And there's like nothing on the other side, right, that is pulling on it. So there's going to be 0 internal force, axial loading, at that end, right? So if assuming a constant cross-sectional area, right? Which, if you look at your modern wind turbines, are they constant cross-sectional area? No, they are not, right? But if it were a constant cross-sectional area, where would this thing fail? Yeah, where it attaches to the rotor in the middle, right? Because it's got all this acceleration yanking on the rest of the blade, okay? And that's all that uniaxial stress that's going to be causing it to want to, separate there. Okay? So it's kind of fun. Now, that's not to say that there are not problems at the tip. What's the problem at the tip? It's unrelated to this class. Huh? Okay, vortex, what else? What's the problem? What is a fundamental limit of propellers on planes? What's that? I see. Yeah. What's that mean? Okay, it can bend. Yeah. All right. All right. So you could have some vibration that's causing this thing to like do some flappiness. Yeah. What is the relationship between velocity and radius? Yeah, it's going way fast out there. And bad things happen when you hit the speed of sound, right? So that's one of the fundamental limits, right? So you might be a design a propeller that doesn't pull itself apart, but at the outside you could have a lot of heating, and you could potentially be very close to the sound barrier at that outer point, as opposed to the inner point, which is like close to zero velocity, linear velocity, that is. Angular velocity, of course, is the same throughout the system, okay? But it's the linear velocity in that case. All right, anyway, let's do it. So the radial acceleration, I give you this because I wouldn't expect you to know this, okay? This is r omega squared, but you can kind of remember this from your geometry, or not geometry, from your physics, right? Kind of remember this, right? Like, as the v squared over r, right? Remember that? Yeah, okay. So that's r omega squared. And what is the r? Well, I'm defining x, again, as being, well, actually, the last one I didn't define it this way, but this time I'm defining it as coming from the outside. Actually, the last time, did I define it from the outside? No, I defined it from the top. This time I'm defining it from the outside, okay? So this is the acceleration, the radial acceleration, okay? And when I mean radial, I mean along the blade, And then, so then what is the externally applied distributed force? Okay, so there's acceleration. Now I got to figure out what the force is. Well, remember, before the distributed force, the little f, right, the Newton that has units of newtons per meter, what was that? It was rho GA. Remember the little f, not the f, the big F, the little f. So you got an idea here that the distributed little force is going to be not rho g, okay? Although yes, you could argue, oh, if there's gravity going down, when it gets down to the bottom, the gravity is going to be high, the acceleration is, again, we're ignoring that type of gravity for this type of problem. Okay, previous the hanging thing, we did keep in track of gravity from the Earth or whatever planet you might be on, or big hunk of mass you might be on. But here we're saying that it's just going to be due to the acceleration of the from the angular velocity, the radial acceleration. Okay, so we can now substitute that in, and we have this expression. So this is nice. This is probably the hardest part of the problem. Okay, again, that the little distributed f. If I didn't do it so much this time, if you're stuck on what that is in the exam, start playing with the units. It's got to be newtons per meter. It's got to be newtons per meter. Okay. So what is the internal force P? Well, what do we got to do? We better do some equilibrium. So here we've taken a slice, all right, and we're exposing the left side, and this is in tension. So I'm going to go ahead. I mean, even if I wasn't, following the convention, if I take a slice, then the direction, right? I usually draw an internal force, an internal axial force, perpendicular and out of that surface. But we also know that since it's in tension, P is going to be going that way. And we also know that we have this this distributed force, okay, that's coming out here. And you know, it's a little bit, it's interesting too, right? Because you're like, oh wait, you know, actually when x is equal to 0, that distributed force is really high. True statement, right? Because as you get farther and farther, it's really high. But if it has no mass to work on, it doesn't matter. Okay? So, what do we do here? We write out, so now we have this equilibrium, p minus the integral f dx. And I sliced here, right? It's probably nice to slice this direction because now I don't have to worry about the reaction force, right, at the center. Because it's not trivial to calculate what the total reaction force is, actually. Okay? It's easier to do it afterward, okay? But it's not super trivial to do it now, right? Because like once I solve everything out, the internal force, right? If I do this out, I mean, I guess it's not that hard because now I know what it is. It's the integral of f dx, right? And so I solve this all out, and so now if I plug in, you know, x equals L. Right? Now I know what the total force is acting on this thing because of acceleration, right? I plug in, so I get L squared minus 1/2 L squared. So it's L squared over 2 times omega squared A times rho. Okay? That's the total, that would be the total force at the middle. And of course, at the right end, or, you know, at the tip, we want here, that force is equal to 0. What do we do? We just plug it into our constitutive equation. What is the overall change in the length of the bar? This is the easy part. The integral is the easy part because we've now got a great expression for p, and we just write it out like that. Okay? And voila. This is the answer now. Okay, so there you go. This is not something anyone remembers. Okay, but it's something that you can calculate. And something that you will get to calculate on the homework. Woohoo! Okay, so there are a few homework problems. What did we do today? We went through volumetric strain and dilatation. Dilatation. It's kind of like dilation. Bulk modulus, safety factors, and distributed axial loading. I hope you liked it. Let's do the attendance. And I will see you all on Tuesday. How do I do this?